Harmonic Vector Excitation Coding. Harmonic Vector Excitation Coding, abbreviated as HVXC, is a speech coding algorithm specified in ms.4 Part 3 ms.4 Audio Standard for very low bitrate speech coding. HVXC supports bitrates of 2 and 4 kbit/s in the fixed and variable bitrate mode and sampling frequency 8 kHz. It also operates at lower bitrates, such as 1.2 to 1.7 kbit/s using a variable bitrate technique. The total algorithmic delay for the encoder and decoder is 36 ms. It was published as subpart 2 of ISO/IEC 14496-3, 1999 mpg-4 audio in 1999. An extended version of HVXC was published in mpg-4 audio version 2 ISO/IEC 14496-3, 1999/AMD1. mpg-4 natural speech coding toolset uses two algorithms, HVXC and CELP code excited linear prediction. HVXC is used at a low bit rate of 2 or 4 kbit/s. Higher bitrates than 4 kbit/s in addition to 3.85 kbit/s are covered by CELP. Technology: linear predictive coding. HVXC uses linear predictive coding LPC with blockwise adaptation every 20 ms. The LPC parameters are transformed to line spectral pair LSB coefficients, which are jointly quantized. The LPC residual signal is classified as either voiced or unvoiced. In the case of voiced speech, the residual is coded in a parametric representation, operating as a vocoder, while in the case of unvoiced speech, the residual waveform is quantized, thus operating as hybrid speech codec. Voiced harmonic residual coding. In voiced segments, the residual signal is represented by two parameters, the pitch period and the spectral envelope. The pitch period is estimated from the peak values of the autocorrelation of the residual signal. In this process, the residual signal is compared against shifted copies of itself, and the shift which yields the greatest similarity by measure of linear dependence is identified as the pitch period. The spectral envelope is represented by a set of amplitude values, one per harmonic. To extract these values, the LPC residual signal is transformed into the DFT domain. The DFT spectrum is segmented into bands, one band per harmonic. The frequency band for the MTH harmonic consists of the DFT coefficients from m-1/2 to m+1/2, A0 being the pitch frequency. The amplitude value for the MTH harmonic is chosen to optimally represent these DFT coefficients. Phase information is discarded in this process. The spectral envelope is then coded using variable dimension, weighted vector quantization. This process is also referred to as harmonic VQ. To make speech with a mixture of voiced and unvoiced excitation sound more natural and smooth, three different modes of voiced speech, mixed voiced -1, mixed voiced -2, full voiced, are differentiated. The degree of voicing is determined by the value of the normalized autocorrelation function at a shift of one pitch period. Depending on the chosen mode, different amounts of band-pass Gaussian noise are added to the synthesized harmonic signal by the decoder. Voiceless VXC residual coding. Unvoiced segments are encoded according to the CELP scheme, which is also referred to as vector excitation coding VXC. The CELP coding in HVXQ is performed using only a stochastic codebook. In other CELP codecs, a dynamic codebook is used additionally to perform long-term prediction of voiced segments. However, since HVXC does not use CELP for voiced segments, the dynamic codebook is omitted from the design.